Okay, in the interest of time, let's get started. We have 2 sessions on moiré. The first talk is by Monica Allen from UC San Diego, who will be talking about scanning probe microscopy of moiré and topological materials.
Great. Is everybody able to hear me? Okay. Well, I'd like to thank the organizers for the invitation to give a talk and for the opportunity to participate in this meeting. So these are the key players who contributed to this work. So on the instrumentation side, my graduate students, Leonard and Chen, have been building up a new scanning probe microscopy system in our lab at UCSD. Taiga is a condensed matter theory student at UC Berkeley who developed some of the models that have really guided our microscopy work on topological states of matter. And then on the materials side, Kixuan is leading our experimental effort on moiré superlattices. I'd also like to acknowledge insightful discussions and collaborations with theorists Yizhuang Yu and Tarun Grover, who are faculty colleagues at UCSD. So my group specializes in a scanning probe technique called microwave impedance microscopy, which can be used to visualize the real space conductivity, landscape, and materials with nanoscale resolution. And because of the wide range of topics that are covered within condensed matter, I just wanted to start by providing a broader perspective on the applications of this technique in different domains of materials research. MIM is very naturally suited for probing materials that might have a spatially inhomogeneous conductivity distribution. So for example, it could be used to measure the evolution of a material across a metal insulator transition by locally detecting the conductivity contrast between coexisting metallic and insulating domains. There's been some success in using MIM to detect emerging electronic states at order parameter domain walls in 3-dimensional bulk crystals like the pyrochloroiridates. It's very natural to use MIM to characterize topological states of matter, which can often host unusual spatial distributions of current flow, such as conducting modes that propagate along edges or domain walls or other kinds of interfaces. So in past work, we've used MIM to directly visualize one-dimensional topological edge states at the boundary of a magnetic topological insulator. There's also been some recent success in the community at doing high-resolution site-resolved imaging of moiré superlattices. And then even more recently, just in the past year, there's been an interesting paper that came out on using MIM to detect quantum valley Hall states in acoustic metamaterials. But in this talk, I'm going to focus my attention on 2 classes of materials in particular, namely topological states of matter and moiré superlattices. So this is going to be a technique-driven talk. Our overarching goal is to develop a suite of complementary microscopy tools that allow us to both visualize and manipulate quantum electronic states at the nanoscale. And there are 2 parts to this research effort. So in the first part, we aim to push the frontier of microwave impedance microscopy into new millikelvin temperature regimes to allow us to gain access to extremely fragile low-energy topological and correlated states. And then the second part of this effort is to develop a method to actually utilize the scanning probe tip to achieve in situ manipulation of moiré materials inside of a microscope. So this is an outline of the talk. So I'm going to just start by saying a few introductory words about the technique of MIM. And then I'll provide a quick update on our recent development of a new dilution refrigerator MIM that opens up new gigahertz imaging capabilities in the millikelvin regime at UC San Diego. In order to provide a concrete example of how MIM can be used to characterize quantum materials, I'll show how MIM can be used to image one-dimensional chiral edge modes at the boundary of a Chern insulator. And then finally, on the material side, I'll talk about our recent work on the development of a technique that achieves in situ manipulation of the twist angle of moiré superlattices inside of a scanning probe microscope. Okay, so the microscope consists of a very sharp metal needle, which you can see here, which we scan over the surface of a material. We can shine microwaves down to this tip via an impedance matching network, and then we can read out the real and imaginary parts of the reflected microwave signal. And so this probe generates very strong microwave frequency electromagnetic fields in a very small spatial region, and MIM effectively is measuring the response of the sample to these high frequency fields. Another thing that I'd like to note is that this setup is designed to have both atomic force microscopy and microwave impedance microscopy capabilities. So as you can see in this picture, the tip is mounted on a tuning fork resonator that serves a dual purpose of providing height feedback for AFM measurements, but also enabling AC mode MIM measurements where we can monitor a signal that's modulated at the tuning fork resonance and filter out signals at other frequencies, which has been very helpful for improving signal to noise. So this is an oversimplified schematic of the measurement setup. So we can use microwave lock-in detection methods to read out the real and imaginary parts of the reflected microwave signal. We're operating this technique in the near field regime where the tip sample distance is much smaller than the wavelength of the microwaves. And therefore, one can quantify the microwave response using lumped element models where the sample capacitance and resistance to ground represent the screening and dissipation terms respectively. So MIM characterizes the local electronic properties of a material by measuring the complex tip sample admittance, which can be given by this expression for this lumped element model. And the resulting response curves show a very dramatic dependence of the reflected microwave signal on the log of the resistivity of the sample, which we're plotting here. So in prior work, we've used the technique of MIM to directly detect chiral edge states at the boundary of a magnetic topological insulator. And in this case, the presence of topological edge excitations is manifested in a very sharp enhancement of the reflected microwave signal at the boundaries of the sample. And this is a system that I'll return to in more detail later on in the talk. Question?
Yeah, quick question. How do I understand the kind of structure between at the interface? Like, why is it not merged into one mode?
Can you repeat the question?
So I think the question was, what is this finer structure at the interface between the two churn insulator states with opposite chirality? And this is something I'll try to get to later in the talk when I discuss these results. But the short answer is that so the y-axis is position and the x-axis is magnetic field. And so we're basically looking at the evolution of the cross-sectional profile as a function of field as you go across this phase transition. So it's not a real space image, and I apologize that the axis label is cut off, which I understand can be confusing. Okay, so in my group at UCSD over the past year and a half, we've really been striving to push the frontier of microwave impedance microscopy to new low temperature regimes that have not yet been explored extensively in this community. And in order to do that, we've incorporated an MIM into a dilution refrigerator, which is shown here. We've integrated all of our scanning probe microscope, as well as all of our cryogenic MIM electronics onto this top-loading probe, which allows for fast sample exchange. And this is a picture of a close-up view of the microscope head and the sample stage. And what you can see is that we've designed the system for simultaneous electronic transport and microwave imaging on the same device. So you can basically characterize the overall conductivity of a material using a transport measurement, and then you can get insight into the microscopic nature of electronic states using the MIM. And so far, we've been able to achieve imaging down to base temperatures of 70 millikelvin. So our dilution refrigerator was delivered to UCSD in January 2022. So over the past year or so, we've been working on setting up this imaging system in our temporary lab space while our lab has been under renovation. So this is a simplified measurement schematic of our low temperature measurement setup. I'm not going to go through all of the details of instrumentation development in this talk, but if you are interested in reading about that, you can check out our preprint that's posted on arXiv right here. Okay, so the first thing that we wanted to do was characterize our atomic force microscopy capabilities at millikelvin temperatures. And in order to do that, we performed a topographic imaging on a test sample using a tuning fork-based height feedback. So this is our data. This is an AFM image of an etched array of holes that are nanopatterned in silicon dioxide. And this image was acquired at 70 millikelvin. And this is a cross-sectional line cut showing the sample topography, and we can see vertical noise levels in the range of 2 to 3 nanometers, which really isn't that bad given that this is a cryogen-free dilution refrigerator where we really have to fight against mechanical noise that's coming in from pulse tube vibrations. So next we wanted to demonstrate the combined AFM and MIM capabilities at millikelvin temperatures. And in order to do this, we did both topographic and electronic imaging of a test sample that just simply consists of a graphite crystal that's exfoliated onto an insulating silicon dioxide substrate, which you can see in this optical image. And so in the MIM data, we can observe a very sharp contrast in the MIM response across this interface between graphite and silicon dioxide. And this arises due to the large difference in the underlying conductivities of these two materials, as one would expect based on the theoretical response curve that's calculated at our measurement frequency at 1.8 gigahertz. Okay, so going beyond simple materials, we also wanted to see whether we could use this system to detect topological edge states. And so in order to do that, we performed MIM imaging of a cadmium arsenide thin film in the quantum Hall regime. So first, what we did was we tuned the Fermi energy into the gap between two Landau levels, and what we observed is a local enhancement of the MIM response at the sample edges due to the presence of edge states. And this is a cross-sectional cut of this two-dimensional image. And then for comparison, we tuned the Fermi energy to be off one of the quantum Hall plateaus, and we observed a very spatially uniform MIM conductivity profile. And all of this behavior is fully consistent with the expected MIM response of a standard quantum anomalous Hall insulator, and it is consistent with existing data or existing experiments that have already been performed on gallium arsenide in the integer quantum Hall regime. So I want to point out that the purpose of these measurements was not necessarily to unveil new physics. The purpose was really to try to characterize the performance of this microscope using well understood materials with well-characterized electronic properties.
Why are the peaks so broad?
Yes.
4 micrometers is huge
That's a fantastic question, and that's actually
Can you
been a
repeat
puzzle.
the question,
Oh, sorry.
please?
So the question is, why are these edge states so broad? And that's a great question, and it's actually been a mystery in the MIM community for many years, because this has been seen in a lot of different kinds of samples, like quantum Hall samples, quantum anomalous Hall samples, and so on. And we have developed some models that can explain this edge profile, which I'll discuss in a few slides.
Sorry, can I ask a question?
Yes.
Is the device grounded somewhere?
Yes. Yeah, the device is grounded. Okay, so we've also gone through some work on optimizing our signal to noise and our image quality, and worked on noise mitigation. I'll spare you the technical details here, but if you do want to read into that, you can feel free to check out our preprint on archive. Okay, so now I want to talk a little bit about how MIM can be used to visualize one-dimensional topological edge states. So one of our overarching goals is to develop new microscopy tools that can shed light on topological states of matter, and driven by advances in synthesis and in theory, there have been a string of experimental realizations of quantum analogs of classical Hall effects, and a few examples are provided here. And what you can see is that all of these two-dimensional systems have one-dimensional topological edge, extremely robust one-dimensional edge states that are topologically protected from backscattering. As you may know, a lot of the foundational experiments on these systems were originally performed in semiconductor heterostructures grown using molecular beam epitaxy, like gallium arsenide quantum wells and mercury telluride. But one exciting new development is that this family of topological materials has been growing, and there have been recent experimental realizations of all of these topological phases in two-dimensional materials and in moiré crystals, and you'll hear a little bit more about that in the next talk. So also just to provide, I guess, a little bit more broader context, there's a lot of people in the community who are very interested in harnessing these very robust topological edge states to enable new forms of topological quantum computing. So for example, there are theoretical proposals for mesoscopic devices that couple S-wave superconductors to one-dimensional topological edge states to allow for experimental realization of non-abelian excitations, which could potentially be utilized to perform braiding operations. And this is an extremely ambitious goal that many groups are working towards using many different materials platforms, but there's still a lot of work that needs to be done to achieve this vision. And part of that work is to gain a better fundamental understanding of the behavior of topological states at microscopic length scales. So in my group, we hope to use this technique of MIM to provide this type of microscopic insight by visualizing edge states in real space. So within the microscopy community more broadly, there have been great strides on the detection of edge states in topological materials using a wide range of probes ranging from STM to scanning, quantum interference, magnetometry. But many of us face a common challenge, which is that it can be very difficult to distinguish the experimental signatures of a topologically non-trivial edge state from a trivial edge state that might originate from band bending or local edge doping. Furthermore, many microscopy techniques are very good at detecting the presence of states at the boundaries of samples, but you can't really easily extract information about the underlying topological characteristics of these states, such as the Chern number or the chirality. So motivated by some of these questions and challenges, my group was also interested in developing a more general theoretical framework that could provide a roadmap for disentangling the experimental signatures of topological surface states from trivial states using the technique of MIM. So in order to provide some motivation for this direction, I want to start by providing a quick overview of some of our prior experimental work on imaging topological edge states in magnetic topological insulators. So this was done in collaboration with the Shen and Goldhaber-Gordon groups at Stanford, and we received materials from the Tokura lab at the University of Tokyo. So the focus of these experiments is on the quantum anomalous Hall effect. Quantum anomalous Hall systems exhibit very similar chiral one-dimensional edge transport as you would observe in a nu=1 quantum Hall state. And the quantum anomalous Hall effect was first experimentally realized in three-dimensional topological insulators with magnetic dopants that break time reversal symmetry. So this is a schematic of the materials that we studied in our experiments. So what we can start with a bismuth antimony telluride three-dimensional topological insulator, and then we can sandwich it between two magnetic dopant layers, which are labeled here in orange. And the basic idea is that the surface electron spins in the surface state of the topological insulator will interact with the magnetic moments in the dopant layers via an exchange interaction, and this will open up a gap in the surface Dirac cones. And furthermore, there's also a hybridization gap that will open due to coupling between the top and bottom surface states. And all of these effects can be captured in the following Hamiltonian, where delta T and delta B are the exchange-induced gaps that are opened on the top and bottom surface states respectively, and delta H describes the hybridization. And upon application of an external field, you can induce a topological phase transition from a trivial gap state into a quantum anomalous Hall phase. Okay, so we tried to probe this physics experimentally in these chromium-doped bismuth antimony telluride thin films. And so this pair of plots shows our transport characterization of the material. So this is the longitudinal conductivity as a function of field, and this is the Hall conductivity as a function of field. And the main feature that we see is very robust quantization of the Hall conductivity at integer at plus or minus 1 e squared over h, where the sign depends on the direction of the magnetization in the film. And we can also see hysteresis that depends on the direction of the magnetic field sweep. So these transport measurements are really our baseline measurement to assess the material's quality before moving on to the microwave imaging step. Okay, so after performing the transport characterization, we can apply a large magnetic field that's deep within the quantum anomalous Hall regime, and then we can scan our MIM tip over the sample. And so this plot here shows a cross-sectional line cut of the MIM response as a function of position. So the vertical axis here is position. And what we can see is that at high magnetic fields in the quantum anomalous Hall regime, we see a very sharp peak in the MIM response at the boundary of the sample. And then furthermore, what we can do is apply a magnetic field to go across this topological phase transition and close the gap, and we can monitor how this edge state profile evolves as you go across these phase transitions. So this is a summary of the experimental observations within this sample. I'm not going to go into all of the details of the experiment, but if you want to read more about it, this is a reference to the publication. So this is one of many examples of MIM studies of topological states of matter. There's also been some really nice work from other labs on visualizing integer quantum Hall states in graphene, and even more recently visualizing boundary conduction in quantum spin Hall candidate tungsten ditelluride. However, one limitation is that this lumped element model that I presented at the beginning of the talk, while it's very effective at characterizing the MIM response of conventional metals and insulators, it doesn't necessarily generalize to describe the MIM response for topological states of matter that are defined by a conductivity tensor. So this really motivated our development, our interest in developing a more general theoretical framework that could predict the MIM response for more arbitrary quantum materials. And I want to acknowledge that this was really a direction that was initially inspired by conversations with Alan McDonald when we were talking about this data set and trying to understand the edge state profile. Okay, so this was a direction that was led by Taiga Wang, who's a very talented graduate student at UC Berkeley. And one of his main results was that he was able to develop an expression for the MIM response of arbitrary quantum materials within linear response theory. So what he was able to do was write down an expression for the complex tip sample admittance, which is the quantity that we're measuring in the experiment, and he could relate that to the dynamical charge density correlation function in the material. And if you want to read, so this is one of the first main takeaway messages of his work. I'm not going to go through all of the details, but if you're interested in reading more about it, you can see this preprint that was recently posted on arXiv here. Okay, so to demonstrate a concrete application of this model, so Taiga used this model to try to calculate the MIM response to these chiral edge states at the boundary of a Chern insulator. And his main finding was that this sharp enhancement of the microwave response at the boundaries was due to the presence of edge magnetoplasmons that were circulating around the perimeter of the sample. And these are basically charge density fluctuations that are circulating on the sample perimeter. And it's not really a new concept. Edge magnetoplasmons have been studied fairly extensively in the context of like quantum Hall and fractional quantum Hall effect in gallium arsenide in the gigahertz regime. So there's actually a very large body of theoretical work on edge plasmons and at gigahertz frequencies in quantum Hall systems. And another good thing that we noticed was that there's at least good qualitative agreement between his theoretical predictions and our experimental observations. So one of the predicted experimental signatures of these edge magnetoplasmon excitations would be the appearance of a sequence of resonance peaks in the frequency domain. And these would be picked up when the tip is positioned directly over the edge state. And this interesting frequency dependence is really what allows one to distinguish the MIM response of a topologically non-trivial edge state from that of a topologically trivial state, which would be expected to be featureless in the frequency domain. So this really motivated our interest on the instrumentation side to develop a new type of pump probe time-resolved MIM in which we could apply fast pulses to local gates in order to excite edge magnetoplasmons in the sample and look at their time evolution. And this should give us a little bit more access to kind of the underlying topological nature of these states, including Chern number, and the line width of these resonances also gives you information about dissipation along the edge. So also, just to return to the question that was asked earlier, so normally we think of the edge state we were talking about quantum Hall data earlier, but normally we think of the edge state of a quantum Hall system to be determined by the magnetic length, which is usually tens of nanometers. We're observing something much more broad in our data, and that's because the relevant length scale that characterizes the width of these edge states is determined by the momentum of the edge magnetoplasmons. Okay, so I want to shift gears and spend the rest of the talk focusing on moiré superlattices, they're a very exciting new platform for exploration of flat band physics. So moiré superlattices can be formed in stacks of 2D materials with rotational misalignment, which can result in a long wavelength superlattice. These artificially layered systems can be created in the lab by isolating single atomic layers from a bulk crystal and stacking them in a precise configuration using micro-manipulators and rotators. So one of the first exciting discoveries in this field was that, at least in twisted bilayer graphene, at small rotations that yield flat bands, electronic interactions should dominate over the kinetic energy. And this gives rise to a very rich phase diagram of correlated and superconducting states that have been observed in experiment. So this plot here shows, this is experimental data showing the measured superconducting domes in twisted bilayer graphene at a variety of different twist angles. So each of the different colors refers to data that was collected in a sample with a different twist angle. And the main takeaway message from this data is that the phase diagram is extremely sensitive to twist angle, where you observe this maximum TC at the magic angle of 1.1 degrees. So this extreme twist angle sensitivity really motivated our interest in trying to develop a technique that allows extremely fine control of the twist angle, fine control of the twist angle in situ in an active device structure. So before I go into our results, I wanted to mention that there's actually been a long history of interest in mechanical manipulation of van der Waals materials in the community, going back many years now. So going all the way back to 2016, there have been some nice papers where people have used an AFM tip to manipulate multi-layer van der Waals crystals like graphite and multi-layer HBN in order to create twistable interfaces. There's some really beautiful work that recently came out of Corey Dean and Jim Hohn's groups at Columbia, where they were able to demonstrate strain and angle gradients that you can create by bending graphene nanoribbons. And also just this year, there was some really creative work that came out of Shahal Alani's group in Israel, where they were able to achieve angle-resolved tunneling in a moiré system by looking at two independently contacted monolayer flakes. So for this project, the desired features of the system that we want to build is we want to be able to develop a technique that can achieve rotation of a single layer of atoms inside of a microscope without deformation of the underlying superlattice. We'd like to be able to access flat bands at small twist angles. We would hope to have angular control with sub-degree precision, and we want a system that's compatible with spatially resolved imaging. So this is a very quick illustration of the technique. It's actually quite simple. So the idea is that you can start by creating a stack of double-layer graphene. You can use conventional nanofabrication techniques to pattern a metal frame on the top layer, and then you can apply an in-plane force using an AFM tip to freely rotate the top layer with respect to the bottom layer. So the purpose of this metal frame is really to provide structural support and rigidity to prevent the flake from tearing or prevent unwanted strain during the rotation process. And additionally, you can see that there's a hole in it that's cut in the middle, and that's to leave the moiré superlattice fully exposed, so you can come in with an optical probe or with a scanning probe tip to do spatially resolved imaging of the moiré superlattice before and after the manipulation. So that's really all there is to it. So this is like a cartoon view of the process. So we use standard techniques to transfer one layer on top of another. We use nanofabrication to pattern a metal frame on the top layer, and then we come in with an AFM tip and push on this handle to rotate the top flake with respect to the bottom flake, and we can do this multiple times to explore multiple twist angles. So this is an AFM image of a completed rotor device, which is shown here. And so we can push on the rotor frame at the location of this white arrow, and this will introduce a change in the relative twist angle. And in order to see this more clearly, this is a superimposed image that contains both the before and after AFM images, where you can very clearly see the change in twist angle. So we intentionally did this with a very large angle so that you can see it by eye. Another small thing that I wanted to mention is that depending on the location of the push point, you can introduce either controlled rotations or lateral translations. So if you take the AFM tip and push in the middle, you can move the top flake laterally with respect to the bottom flake. But our interest was primarily on the angular control, so we focused on this top sequence. Okay, so this is the final data set in this section of the talk. So in order to demonstrate direct control over the moiré superlattice periodicity, what we did was we performed very high resolution piezo response force microscopy of the moiré superlattice before and after rotations in order to read out the induced change in the twist angle, and we could also evaluate kind of the overall kind of periodic structure and strain within the moiré superlattice. So this is a sequence. This shows the data that we acquired after a sequence of rotations. So we start with the two flakes in a roughly angle-aligned geometry that gives you a very large period moiré superlattice. We can introduce a 0.01 degree rotation, which brings you here. And then we can introduce larger rotations. So this is an example of a 0.3 rotation and a 0.83 rotation. So this is really the main experimental result that I wanted to share. It's a fairly straightforward and simple idea, but since doing this, we've also been trying to generalize this approach to also apply it to twisted TMD homobilayers as well, because there's a lot of really interesting topological phases that have been predicted as a function of twist angle in these systems, and you'll hear a lot more about that in the next talk. Okay, so I think I'm almost out of time. So in summary, we've tried to put together a toolbox of complementary microscopy probes that allow us to combine tunable twistronics with imaging. And so these are the three tools that we have in our toolbox. So the first is high-resolution nanoscale mapping of the spatial structure of the superlattice, which we do with the piezo response force microscopy. We also have in situ manipulation of the twist angle and active devices inside of a microscope. And then finally, we can combine these with mesoscale imaging of topological and correlated states at millikelvin temperatures using microwave imaging. And our hope is that the combination of these imaging tools might help us to rigorously connect the underlying lattice structure with the electronic ground states that are observed at low temperatures. Okay, so that concludes my talk. Thanks very much for your attention, and I'd also like to thank our team of experimental and theoretical collaborators that contributed to this work.
Okay, thanks for a great talk. We have time for a few questions. Back there.
Very nice talk. I have a question about how do you differentiate the topological edge state from trivial edge state, for example, just doping.
Can you repeat the question, each question?
Oh, okay. So the question was, how could MIM be used to kind of unambiguously differentiate the signatures of a topologically non-trivial edge state from a trivial state that's due to band bending? Yeah, and so the answer to this comes out of Taiga's models. So the expected MIM responses in the frequency domain for a topologically non-trivial edge state should show this sequence of EMP modes where the positions of the resonances are determined by the Chern number and the sample geometry. So this is the experimental fingerprint that you would expect for a topologically non-trivial state. By contrast, if you had a trivial state that was where you had an increase in conductivity due to a doping profile or band bending, you would expect the MIM response to be featureless in the frequency domain, and you wouldn't see the resonances.
I know that's just a standing wave, but the standing wave always have resonance from the band. The wavelength is kind of one over integer of the whole circle of the
Well, I mean, based on our models, there's a very distinct frequency dependence that you would get based on doping, trivial doping versus this. But if you want to talk about it in more detail, I can go through the results with you later.
So I had a question about your new method of generating these twisted structures. Yeah. So one of the problems in the existing method is you get large strain sometimes in these. Typically, you do get strain samples, and with your method, do you think you could avoid those issues? And or when you measure, could you actually characterize the strain?
Yeah, that's a very good question. We can get some insight into strain and asymmetries in the moiré superlattice directly from the PFM images. So I have some kind of anecdotal observations that we haven't really explored extensively in many samples. But one thing that we did notice is that if we do imaging of a moiré superlattice immediately after sample fabrication, we do often will notice like kind of a deformation or intrinsic strain within the moiré superlattice. But we do notice that after doing this in situ manipulation step, we often see much more ordered and periodic moiré superlattices. So it's almost like this rotation process might be relaxing some of the strain. We've only seen this in a couple samples though, so I don't know if it's systematic or if we just got lucky. The other thing that we noticed is that the symmetry of the moiré superlattice that we get depends a lot on the design of the rotor. So it's really important to design the rotor in this way where you build in structural support from all sides. We've also built open rotors where you only have support from one side and the rest is open, and then you get a lot of strain and deformations of the moiré superlattice. So that design is really critical for keeping strain under control. So we haven't done like a systematic study, but those are our early observations.
I had a question. Okay, sorry. Yeah, I had a question about we were talking about the width of the magnetoplasmon. Where did the K come from? What sets the scale?
So it does depend on the Chern number, and I believe the measurement. I think that
it's some longish wavelength, right? So
yes.
What's that coming from? It's related to the frequency of your probe, or?
The wavelength, the expected decay length depends on a few things. So one of them, it does depend on, I believe, the Chern number of the edge state at the boundary, and I think that it also depends on sample perimeter and the frequency. And we do have like a full expression for that value, which I can show you in our manuscript, but I don't remember.
The width of the state will actually depend on the sample dimension? Right?
Yes, so you expect much higher EMP resonances. I think there's like a 1 over perimeter dependence, so the smaller the sample, the higher the EMP resonance is going to be, and you're going to end up with a much sharper edge profile. So there is a geometry dependence there. But we have, like, I think, a full expression in our manuscript, and I can show you.
Thank you.
Here.
Any further questions? No? If not, let's thank Monica again.